The combination of a uniform flow and source can be used to describe flow around a streamlined body called a half-body. Assume a certain body has the shape of a half-body with a thickness of 0.5 meters. If this body is placed in an airstream moving at 20 meters a second, what source strength is required to simulate flow around the body? So, to begin, we want to start with the equation that determines the width of a half-body, which we will call W. So this is half-body width is equal to 2 pi b. And this is simply something you have to know. You have to just be able to pull this out. And from here, this will begin to come together. So we have W, the half body width, is equal to 2 pi b. B is defined over here in this diagram as the difference or the distance between the source and the stagnation point. Both of these diagrams depict the same phenomenon. This is trying to give a physical representation of what's going on, where we're using a source in the middle and a airstream to create a stagnation point and thus simulate a half body. So we can actually reorganize this because we have the prescribed half body width, and we can reorganize this to get B, which we're going to need in just a moment. So B is equal to W over 2 pi, and we know that W is 0.5 meters, so this is 0.5 meters over 2 pi. All right, we're going to need that in just a moment because we're going to now go to the velocity field for a 2D source flow, because obviously we're using a source flow here. And so we're going to go here and get the velocity field for 2D source flow. All right. You should also know this equation. This is V of R is equal to Q over 2 pi R, where Q is the source strength, VR is the velocity at a given radius, and R is the radius that you're evaluating this at. So what we want to do is we need to find the strength required to create this respective stagnation point. And so we're going to need the velocity at this point produced by the source to be equal to the airflow or the airstream velocity, because then they will cancel out and that will create the stagnation point that will then form the rest of the half body. So we have a half body dimension that we can use to pull all of this out of. And so because we're looking for the strength of the source, we are going to isolate for that. And so this equation will very quickly become a very simple one, where we have Q is equal to VR times 2 pi R. And again, VR will become the uniform flow velocity, and R will be the distance we evaluate that at, which is up here because we have that. B is this distance, and R is a distance away from the source. So we will plug all of that in. Q is equal to 20 meters per second times 2 pi. And then R is 0.5 meters over 2 pi. And so 2 pi's will cancel out. We have 20 meters per second times half. So we have 10 meters squared per second is the strength of the source required to produce this stagnation point representative of this half body.